Hello, 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 everybody, and welcome back. Root Beer here, looking at question number 7 on the grade 7, 2008 Gauss paper. So let's dive in and have a look-see. Question 7 down here. Which of the following is a prime number? Okay. So we might remember there are prime numbers, there are composite numbers, and there's also the number 1, which doesn't fit into either category. A composite number is one that can be written as a product of two things, neither of which is 0. Okay? It has factors other than 1 and itself, whereas a prime number doesn't. There's no way to break a prime number down into smaller numbers. Okay? There's nothing you can do. And we need to sort of remember that definition. Either that, or because we only go up to 27 in this question, we could, I suppose, just memorize a whole bunch of primes. Okay, I find it useful to know the primes up to 100. I've just found that's useful, not even for math contests, just for math that I encounter in my life occasionally. And so, if you want to devote time to memorizing the first prime numbers up to 100, there's 25 of them, 2, 3, 5, and so on. That's fine. But if you're not a memorization person, if you're just, I want to understand the math, I want to be able to do this question, even if it were answers of 520, 521, 523, 525, and 527, which would make this question a lot harder, what can I do? Well, how can I understand? Well, remember that prime numbers can't be broken down. And so you might say, well, is 20 a prime number? And if it's not a prime number, it's a composite number, and I can break it down. So does 20 have factors? And yeah, I could split 20 just off the top of my head. It's a multiple of 2 because it ends in a 0, 2, 4, 6, or 8. So 20 is 2 times 10. Those are two smaller factors. So 20 can't be a prime number. And so if I just remember that, if I remember the definition of a prime and a composite number, I can just go through this question and say, oh, that has a factor of 2. Oh, this has a factor of 6, and things like that. All I need are some factors. Okay? And the ones that I can't factor, the ones that I have trouble factoring, I can always break out my calculator if I need to. But, the ones that we can't factor in the end are the prime ones. That's how it works. So, let's just write down some factors here. So we've got 20, 21, 23, 25, and 27. Now, I know my primes. You possibly know your primes, so 23 is the answer. So we'll just go in pencil C, and if you're someone who just memorized them and aren't interested in factoring, feel free to skip to the next question. The answer is C. But if I went through them and I said, okay, 20. 20 is a multiple of 2. It's 10 times 2. Automatically, that makes it not prime. Okay. 21. Well, it's not a multiple of 2. In fact, none of the remaining ones are even numbers, so they're not multiples of 2. Now, we might remember 21 is 7 times 3. A good way to test whether or not something is a multiple of 3, add the digits. Okay? 2 plus 1 is 3. If adding the digits gives you a multiple of 3, the number's a multiple of 3. You don't even need to actually write out the other factors. As soon as you know it has a factor of something like 3, or 5, or 7, or 11, something like that, automatically you know it's not prime. Okay. 23, 23, we can think about it for a little while, but it just doesn't really work for us. So we might declare, oh, this one must be prime because it's really hard for me to think of a factor. But it's really hard for me to think of a factor is not a proof. And if we made this question hard, if we made the numbers bigger, you might just be missing something. I'll talk about that in just a moment. But, we find it hard, so we'll skip over it. Maybe there's an easier one to rule out. And we move over to 25. 25, that's a perfect square. He's 5 times 5. So he's not prime. And 27, once again, 2 plus 7 is 9. That's a multiple of 3. 27 is a multiple of 3. And indeed, it's 3 times 9. 27 is actually 3 cubed. 3 times 3 times 3. But we don't need to know that. We just need to know that there is a factor. And so it's not prime. So by process of elimination, 23 has to be the prime unless I've messed up my factorings. Okay? And 23 is the prime, but how do I know for certain that a number that I find is difficult to factor, that I just can't think of a factor, and the calculator isn't doing anything for me? How do I actually know it's a prime? Okay, so here's how we do it. We get our calculator out often. Imagine the numbers were bigger, and what I do is I square root 23. So square root of 23 is 4.79. If we were looking at a bigger number, like, I don't know, 621, and I wanted to figure out if that's prime, 621 has a square root of 24.9. So, I take a look at every number, every prime number up until that square root, up to and including that square root. So for 23, it was 4.7. So what I do is I go through and I say, what are the primes between 1 and 4.7? Well, there's 2 and 3. And then I ask, well, is 23 a multiple of 2? No. Is 23 a multiple of 3? No. Well, that's enough to then declare, oh, this guy's not prime. Take a look at with 25. So the square root of 25 is 5. So what are the primes up to 5? 2, 3, and 5. Is 25 a multiple of 2? No. Is it a multiple of 3? No. But it is a multiple of 5 twice. And so we eventually find a multiple there. Let's pick a bigger prime. How about 37? Okay. 37 is a little more than 36, so it has a square root of 6. Well, 6 point something. So 37 has a square root of, let's say, 6.1. I have no idea if that's actually what it is. It's more than 6. So what are the primes up to 6.1? 2, 3, 5. Is 37 a multiple of 2? No, it's not even. Is 37 a multiple of 3? Well, no. Add the digits. It's not a multiple. The 3 plus 7 is 10. It's not a multiple of 3. Is it a multiple of 5? Well, no, it doesn't end in a 0 or a 5. So 37 isn't a multiple of 2, 3, 5. At that point, I get to say, aha, this is not prime. Or sorry, aha, this is prime. It's not composite. Okay, and it works for bigger and bigger and bigger numbers. Try it out with something like 121, which is composite, and try it out with something like 107, which isn't. With 107, the square root's just a little over 10, so I just need to divide it by 2, 3, 5, and 7 to confidently declare that it's not prime. And, the question's been over for quite a while, but let's just address one final thing. You might say, well, how do I know what are the primes up to that square root? And, well, the exact same method would work. I do something like square root of 89. And that's a little bit more than 9. So 2 is a prime, 3 is a prime, 5 is a prime. I can't remember if 7's a prime. Square root 7. And it's about 2 point something. So I divide 7 by all the primes less than 2 point something or other. 7's not a multiple of 2, so 7's a prime. So I would then try and divide 89 by 7. And it's a very algorithmic process. This really lends itself to computer programming. I'm not going to address in this video, because it's already gone on kind of long, why this works, why the square root, you only need to include up to the square root to make it work. That's something for you guys to work out based on the definition of what a composite number is. And, there's some other math involved there, some inequalities you can justify. But the video's gone on kind of long for a grade 7 contest question, so we'll just end it by saying the answer is C, 23 is the prime number. Alright. I will see you guys in the next video. Until then, take care.